Welcome back. Let's talk about formal logic. Here's the agenda of what uses logic, what is an argument. Then we're going to develop a series of concepts here slowly and then circle back to what is an argument. All right, so let's get started. So the first couple of pages of these notes are kind of philosophical, and you can spend as much time or as little time as you want on that depending on your interest. I think this stuff is kind of fun. In fact, I started out as a philosophy major in college, and I had to change my major when I realized that someday I'd have to get a job. But I still think it's fun, and I still read philosophical books and think about this stuff a little bit. But let's go through this kind of quickly and try and relate it to what we need to understand for computer science. All right, so I'm doing that by asking this question, right? Because a question is a good way to tease something apart and break it up and try and understand it. So the question is, why study formal logic? Okay. So reason number one, computers run on logic. That is, when a program's running, all it's doing is logic and arithmetic operations. That's it. So that's actually the very definition of computing is logic and arithmetic. Okay, we've all written programs where you use logical statements like if A is less than B and C is less than 2 or something like that. So you use logic in programs, and at the hardware level, you can actually think of the circuits themselves as solidified logic. There's these little things called gates. There's AND gates, OR gates, and other kinds of gates. And they actually implement a logical operation in silicon. So you can think of that as kind of a solidified logic. All right, at the other end of the extreme is something called, there's formal methods. I'm not sure what they call them, but they're formal methods that are used to evaluate the correctness of computer algorithms. Now, you know from writing code that there's two kinds of errors, right? There's syntax errors, and then there's what's called logic errors. So syntax errors, the compiler will spit out something to you, and you got to put in a semicolon somewhere or a missing parenthesis or something like that, right? And then you get your program to run, and it might still be wrong. So, we call logic errors runtime errors, right? So your program will compile and run, but it's still wrong. So it turns out that from philosophy or whatever, there exists these formal methods that could be used to determine the correctness of a program, or they could find logical errors. Now, it doesn't work right now, but it's important to think about this because the syntax error stuff, that works. Your compiler will find your syntax errors, no problem. But logic errors, right now, there really isn't any way to find all the potential errors that are in your code. But if there were, that would be a huge deal, because right now, programmers spend the bulk of their time just finding logic errors, right? Not writing code, but fixing code. So if somebody can invent a formal method to find these kinds of logic errors, that is a program that checks your program to see if it is logically correct, that would change the industry completely. It might result in a lot of jobs being lost. So that's something to keep in mind. All right. Another thing that is drawn from formal logic is this idea of expert systems. Now, this is an artificial intelligence technique that uses logic, and it kind of simulates a certain kind of human behavior. And generally speaking, when a computer simulates a certain kind of human behavior, we call that artificial intelligence. That's one of the definitions of artificial intelligence. The whole idea of what is artificial intelligence is a big subject, but it does break up into different kinds of subfields, and one of those is something called expert systems. All right, so that uses logic. Also, there are classical limitations of logic. Now, we'll get into that in these notes, but think about the kind of logic statements you've written in your program. They're not that long typically, right? Like you might have something if A and B, or C, something like that. These don't get to be super long, but in formal logic, they can be quite elaborate. And when they get that big, they'll tend to have problems. In fact, they'll have problems even when they're small. Okay, so the study of formal logic can help us understand things that can go wrong with simple logic as well as more complicated logic. All right, so that's one reason to study this stuff. Okay, reason number two, just real briefly, there's a kind of a duality here in the universe, so to speak. There's computers on the one hand, which are completely logical, and then there's humans, which are not logical. And as computer scientists, we have to develop interfaces so that computers can talk to humans. And presumably, as these interfaces get more sophisticated, they're going to have to become more human-like. That is, presumably more tolerant of the non-logical kind of things that humans do. All right, there's a guy that wrote a book, Facing the Intelligence Explosion, this Luke Muehlhauser guy that could explain this stuff a lot better than I ever could. If you have an interest in that, you can read that. All right, that's another reason to study logic. All right, reason three, how do we create AI? So, that would really require us to understand how humans think. And humans think in all kinds of ways. Only a tiny part of that is logical. There's all kinds of ways. So, studying logic is part of it, but there's a lot more to it. And once again, there's a guy that could explain this a heck of a lot better than I could. There's a book, a very good book called On Intelligence by Jeff Hawkins. And this guy had a hardware background developing memory systems, if I remember correctly, memory systems in computers. And so he looked at the human brain structure and function as a memory system. And he was able to contribute some insights because of his perspective in hardware that are very interesting. Anyway, a little bit philosophical, and if you have an interest in this kind of stuff, then you can look at these books, or you can read the notes a little bit more clear and think about it, and then definitely read the books for people that know a lot more about that kind of stuff than I do. But don't expect that you're going to be able to get a job. Okay, so let's start getting into some nuts and bolts here. Very slowly here. So what is logic? Here's some definitions. There it is right there. I'm not going to go through those, but okay, let's kind of ease into this and start getting it a little bit more mathy and more nuts and bolts kind of that we can write a program. All right, there's something called an argument. You can think of it like this. There's the argument, which has logic in it. You feed what's called assumptions into it, and it does its thing, and you have conclusions. So it looks like a function. We've seen this before in the function material. And it can be thought of as a function. That is, you can think of the inputs as true, false values. There's some logical operations in here, and then the output will be true or false values. So for example, you could have the set of possible truth values, and I'm using B for Boolean. So you have a set B, which consists of the elements true and false. So you can think of an argument as a function, right? Argument is a function. This is using function notation that maps the set of Booleans back into Booleans. And it might look like this if you have one operand in and then one operand out. In other words, if it's a unary operation, it'd look like this. But if you have two operands in, then you're feeding in an ordered pair, or that is, you're feeding in an element of B cross B into this argument, and you're getting out one Boolean. For example, you could feed in 1 and 1, and you could feed 1, and you could feed the ordered pair 1 comma 1 into this guy. And if this were just doing and, we all know that and produces 1 if you give it two ones. So that would be the second kind of thing for a binary operation. All right, and the domain of inputs can be tuples of any size. So it could, you could have one, whatever. You could have a big old long thing, and then you could have some some argument, and then you could produce one output. All right. So here in classical philosophy, before we move on, they're concerned with form over well, I have to be careful what words I use, but they use the phrase form over function. And what they mean is they're more concerned with the logical structure of the argument than whether the inputs and outputs are true or false, which is a kind of a weird thing, but that's what comes from the classical study of and philosophy. So we'll talk about that a little bit more, but let's kind of move on here. So let's say you have some argument, then you have 3 parts to it. You have the assumptions, you have the logic, and then you have the conclusion. So you can how good are both of these components here, right? Like how good are the assumptions and how good is the logic? So by good, I'm using the term good vaguely so we can define it a little bit better. But for logic, good logic is valid. That is, we use the term valid when we're talking about logic. Okay, so if logic is valid, that's good. Then the assumptions, we have true and false values. So the assumptions could be true or they could be false. So the way you use these things in classical philosophy is you have these assumptions and you have to agree on the truth and falseness of the assumptions. Or let's say you don't have to agree, but one way that it could work is that you agree on the assumptions as true or false, and then you have to agree on the logic being valid. And if you agree on the truth, false valueness of the assumptions, and you agree that the logic is valid, then the argument, or this whole system here, will produce certain conclusions that you are obliged to agree with. Okay, if you agree on this part and this part, then you agree with this part. And that's kind of how it's supposed to work if you're being a good sport about the whole thing. But humans, humans a lot of times will just choose to not believe the conclusions. That's one of the problems with logic. So even though humans will agree with this stuff and they'll agree with this, it'll produce something they don't want to believe and they'll just not believe it. So I'm not being sarcastic. I'm just telling you that's the way it is. So it's something we have to deal with. All right. Okay. But anyway, let's kind of break this up a little bit more, because these assumptions. The assumptions take a little bit more of a precise form here. And they're not just true, false, but they're something called propositions. All right, so let's get into that. So what is a proposition? Okay, a proposition is a declarative sentence that is clearly either true or false, but not both. So here's some examples of just sentences, because there's all kinds of things you can say in English. And, English is complicated language. All languages are complicated, but the point is there's a potential for a lot of ambiguity, and that's a weakness of this whole approach. Quite honestly, this whole trying to treat the world as that humans and humans speaking, talking to each other and stuff, trying to treat that as some kind of machine that we all have to agree with is just, it's not reasonable in my opinion. But anyway, let's look at some English sentences and see if they're propositions or not. So this guy here, hi. Well, that's not a proposition because you can't really assign a true false value to it. All right? You agree with that? Well, I hope so. What about Paris as the capital of France? Well, that's a proposition because we could argue about whether it's true or false, but it's clearly one or the other, right? It either is the capital of France or it isn't. So that's what makes it a proposition, the fact that this is either true or false. Okay, look, there's a difference between being a proposition, that's like one, and then the second thing is that prop true or false? These are two different things. So that's what this table is trying to show here. So like high is not even a proposition, so it has no truth-false value. But Paris is the capital of France. That is a proposition. And most people would agree that its value is true. There might be a few people that would argue with you of whether Paris is the capital of France. They might say that it's not. But it's still a proposition. 1 plus 1 is 3. That's a proposition. It either is 3 or it isn't 3, right? So it's a proposition, and it has a value of false because it happens to, 1 plus 1 is not 3, right? It's false. So there's a difference between whether something is a proposition, and then once you've established if something's a proposition, then you can further establish that it's has a particular true or false value. So some things are not so much propositions, like another beer please or que tal or something like that. Those are clearly not true or false, although you could argue that, okay? And something like this, like I own 8 computers, is that a proposition or not? Perhaps you could. So you know what? This should really be N, and we'll talk about that a little bit. And in classical philosophy, we have a way to handle statements like this that have numbers in them, and we'll talk about it. And part of it is just understanding what they do in classical philosophy, not so much arguing with it, because as computer scientists we have particular needs, and we're just going to use the stuff that helps us, and we're going to let the philosophers deal with all this other junk. But look, so this here I'm just reiterating there's a difference between whether a sentence is a proposition or not, and then if it is a proposition, then it could have a true or false value. So there's 2 different things. That's a sticking point for students, so don't get confused on that, John. But this is important right here. Some sentences are clearly propositions. Like I would say Paris is the capital of France. That's clearly a proposition. I mean, it either is capital of France or it isn't. And then some statements are clearly not propositions, like hi. That's clearly not a proposition because it has no truth-false value. But there's other things, in fact, many kinds of statements where it's not easy to tell whether they're propositions. Okay, now we'll let the real philosophers argue about that. You take a philosophy class, you spend a whole semester arguing about whether something's a proposition or not. You can major, you can, whatever. You could do a semester project in that kind of stuff. We're not going to mess with that stuff. We'll let the real philosophers worry about that stuff. All right, moving right along here. Yeah, so there's this expression, form over content. Classical philosophy, formal logic, subdiscipline, is concerned with form, not contents. That is, we don't really worry too much about the truth or falseness of the assumptions. Like, we don't really care if Paris is the capital of France or not. We're just concerned with building these arguments that could process that kind of information, which is kind of a weird thing when you think about it. But why? I mean, a little historical context. The guy that invented this, contributed a lot to this discipline was this George Boole guy. And what he was trying to do is sort of understand the world or generate new knowledge, perhaps, by just arguing and talking. He didn't want to actually get his hands dirty. So here's what he wanted to do. He wanted to take English, like go to the local pub and sit down with people and just start jabbering, and then turn that into symbolic logic. And then you could do basically math on that stuff. You could do what's called Boolean algebra. And in the end, you could turn that back to English. And he was thinking that we could understand what people are saying, number one, and perhaps we could arrive at some other kinds of truths, I suppose, by doing this kind of thing. So, in my opinion, that is really difficult because language is very complicated and very vague. Like, not only is it difficult to tell if something's a proposition or not, quite often, there's a lot more elaborate kinds of misunderstandings that people can have when they're talking. So just the idea that you could take what people say when they speak and totally analyze it and expect it to be 100% logical, to me is just, I think it's kind of nuts, actually. But who am I? I'm just a regular guy. I'm not anywhere near Boole's caliber. But that's my opinion. All right. It is important to mention here, that's kind of what I'm alluding to. If you want truth of, at least of the material world, let's say, science is pretty darn good at that. It's proven its effectiveness at least understanding how the world, what the world physically is and how it physically works. It's a certain kind of truth for sure. That's definitely very powerful. There's still a place for logic, of course, but science is pretty powerful. All right, so let's kind of move on here. So this guy, George Boole, he wrote this book, The Laws of Thought, where he laid down a lot of this stuff. And what he came up with is this, all of these logical operations. We have a word not, or no, or it is not the case that. You can outright disagree with somebody. No, it isn't. You could write as another phrase we use. No, it isn't. To disagree with somebody. So we call that not. And it has these various symbols, some of which are used by mathematicians, some are used in digital logic, some are used in formal logic. So these are all different symbols for not. And we'll be using them all. And this is the definition of not. If you have an input, you have an output. If you insert false, which is a 0, into the thing, you'll get 1. And if you insert a 1, you'll get 0. So you're all familiar with that. You're all familiar with all of these, actually, right? And then here's and, which he called conjunction. These are the 3 different symbols that we can use. And this is the truth table for and. So and produces truth if both of the inputs are true. And then there's disjunction, which has these symbols. And disjunction produces true if at least one of the inputs is true, right? Just for us coders, we learned this pretty early, this stuff. And then we've got exclusive or, XOR, and it's got these symbols. And it's true if at least one of the inputs is true, but not both. Okay? One or the other, but not both. There's that. And then there's this other one. Now they start to get kind of weird. There's this thing called implication, which is actually the basis of proof by contradiction. So it works very well for certain kinds of things. And in other kinds of things, it doesn't work very well at all. But anyway, here's the truth table. Now, to me, for English, I think this thing is not so good. But I just look at this as a truth table. I don't worry about its meaning English-wise beyond its operation as a truth table, right? Then there's another one called bicondition, which has another truth table. The way I remember TFF is, or implication is that it's TFF. This one row, TFF, or true, false, false. And then the rest are ones. So I just remember TFF, and I can remember this table. And then this guy, bicondition, it's the opposite of XOR. It's like X NOR or NX. I'm not sure if it's X NOR or X in it. I'm not sure if it's that, or I'm not sure which one of these it is. But anyway, this with a not in front of it. Okay. So some of these we use all the time, not, and, or, and XOR we use, and implication and bicondition we don't really use in programming. Let's talk about that a little bit further. But anyway, these are the ones that George Boole came up with in his Laws of Thought stuff. But some of these we care about and some we don't. So that table had 5. In theory, there's 16, right? If you think about, at least for the binary operations, if you think about the binary operations as having a 4-bit column, right? If you, because the inputs are always the same, right? Like the way I've listed them here, I listed them 0, 1, 0, 1. 0, 1, 0, 1, and then for x, 0, 0, 1, 1, 0, 0, 1, 1. So the inputs are always in the same order. The only thing that's different is the output column. And has the pattern 0, 0, 0, 1, or has the pattern 0, 1, 1, 1, etc. So how many patterns are there of 4 bits? There's 16, right? So you could start from 0, 0, 0, 0, 0, 0, 0, 1, which is AND, right? Then you'd have 0, 0, 1, 0, which would, so this would be 0, this is 1, this is 2. There's all the way to 15, which would be 1, 1, 1, 1. And somewhere in the middle is 0, 1, 1, 1, which is, what is that? That's 7, which is OR, okay? So there's 16. Implications in here somewhere and biconditions in here somewhere. There's 16 possible ones of these guys. It's a really good way to think about this, sort of philosophically and also computer sciencey, but here's what it boils down to, I think, is some of these logical operations clearly make sense in English and in coding, for like and or not. Those are simple. Implication and bicondition start to get confusing, especially when they're tied to human spoken language or natural language, so to speak. Okay, there's that. And then there's some others that are not necessarily super easy to understand, but they turn out to be very useful for designing computer hardware circuits. NAND, NOR, and XOR would be in here somewhere. So it brings up the question, there's other theoretical operators, maybe they would be useful, something to think about. Okay, let's go on. So the ones coders care about are AND or not mostly, and then NAND, NOR, and XOR next. But there's others that, in theory, you could mess with. So let's go back to what Boole was trying to accomplish, or what I like to call Boole's trip. He wanted to take spoken English, turn that into symbolic logic, do manipulation on it, that is, be able to do Boolean algebra on it, analyze the structure of the logic, and then in the end, maybe turn that back into English and establish a little more derive a little more kind of truth about the world out of that. All right, so let's look at an example of this. So we have a proposition. So we have to deal only with propositions here because we need things that have a true false value. So P will be a proposition. This statement, it is not the case that, assume P is some proposition, then this statement, it is not the case that P is called the negation of P. So for example, P could be the statement, today is Friday. Then the negation of P, or not P, is another statement, this statement right here. It is not the case that today is Friday. Or in English, you can say this another way. In English, you could say today is not Friday. In fact, that's what people would normally say. I mean, maybe 100 years ago or 200 years ago, people used the expression, it is not the case, more frequently than they do today, but people don't say that very often today. That's one of the pitfalls of this stuff, is that language changes over time. Not only changes over time, but it changes from person to person. Each individual often, or group sometimes, has a slightly different way of talking. So you can't understand what people are saying, and so to be able to to take something so literal that you could do this kind of thing with it is a little bit of a stretch, in my opinion. Anyway, just my opinion. So let's look at a couple of more examples here. So here's the proposition, 2 plus 2 equals 4. So let's go slow here. P is a proposition because 2 plus 2 either equals 4 or it doesn't. That is, it has a true value or a false value. That's enough to make it a proposition. This particular proposition happens to have a value of true. Most people would agree, especially math teachers would agree with that. So we can write the negation of P as this not P thing using this negation symbol. We could read that as not P. That would result in the statement it is not the case that 2 plus 2 equals 4, which you could write in mathematics using this symbol here. 2 plus 2 is not equal to 4. Okay, another example here. It is not the case that Paris is in Rome. So P is the proposition. It is not the case that Paris is in Rome. So the negation of P would be Paris is in Rome. We just get rid of the not part. All right, so that's that. All right, so let's look at another a binary operation. So far we were looking at negation, which is just a unary operator. It just operates on one proposition, just P, right, to produce another proposition. So one proposition in, one proposition out. Let's look at conjunction, which is a binary operation. That is, it takes in two propositions, P and Q. So we write it P and Q, and we call it a compound proposition. We can also call it the conjunction of P and Q. So here's two propositions. P, today's Friday. Q, it is raining today. So the compound proposition P and Q is this statement here: today is Friday and it's raining today. Okay, so here's the truth table for conjunction, and showing, you know, various values of the compound proposition based on the values of the input proposition. So basically, let's say it's not Friday. Like right now when I'm recording this, it's Saturday. So this is false, and it happens to not be raining. So this is the situation today right now as I record this. It's not Friday, and it's not raining. So the compound statement is also false. So if I said to you, today is Friday and it's raining today, I'm lying. Okay, I'm lying to you. And in fact, you know, it could be raining. Let's say it really was raining today, but it's still not Friday. And I said to you, today's Friday and it's raining today. Then Mr. Boole says that I'm still lying to you. And you know, let's say it was Friday but not raining, and I said to you this thing, today is Friday and it's raining today, then I'd be lying to you. Okay, so this is the common understanding, or at least, it is the common understanding. It's certainly what Boole wanted us to interpret this English statement that way, and I guess everybody does. You know, for and, we all agree with that interpretation of and. All right. Anyway, here's some other ones. Just using math instead of English. And this is a little bit more like code, right? What you might write in a program, in an if statement, for example. So in order for this entire expression right here, this compound proposition, the conjunction of P and Q, this statement right here, in order for it to be true, then both of the little propositions P and Q must both be true. So 2 plus 2 is 4, that's true, and 1 plus 1 is less than 3, that's true. So we're ANDing those two together, and we get true for the compound proposition, right? That's the way we think of it in programming with just numeric expressions. You know, if you threw in an English statement in there, then, you know, it would look a little bit like this, but it's starting to look a little bit less like it would compile. But anyway, that's conjunction. So you can think of conjunction as a function, because it's taking a pair of true-false values and outputting a single true-false value. In other words, it looks like here. It looks like this. You're taking an ordered pair of Boolean values and feeding this into this conjunction mechanism, this conjunction argument, tiny little argument, and it produces a single truth false value. So in set theory notation, we have the ordered pair AB is an element of the Cartesian product Booleans crossed with Booleans, right? Where Booleans are just true false values or ones and zeros. And the output C is a single true false value. And conjunction is a function that maps B cross B back into B. So it's a relation given by this ordered pair where you have ordered pairs where the first element of each ordered pair is another ordered pair. Right, so this is the input 0, 0, it produces an output 0, and then the input 0, 1 produces the output 1, like that. It looks like this in the digraph. These are all the possible inputs. It's B cross B. It's the entire Cartesian product is the input, and these three guys produce a 0, and then this one produces a 1. So it's a relation. Relations have properties, remember? Robust and deterministic. This guy's robust because it knows how to handle every element of the input of the domain. So it won't break when you feed it these guys. It's deterministic, that is each one of these inputs will always produce the same output. Like 0, 0 will always produce a 0. There's only one arrow leaving each one of these guys. That's deterministic. So it's robust and deterministic, therefore it's a function. And then we can analyze the function further, and we see what the function is onto. That means it totally covers the range. Remember, the range is all the elements of B. Totally covers the range, but it's not one-to-one because I've got 3 arrows going into this guy. So I can't go backwards, basically. That is, I can't feed a 0 in here and get back to, the same one every time. Okay, so these things can be thought of as functions. These logical operations can be thought of as functions, and most of them do not have an inverse, but I'm not sure if some do. I'll leave that up to you to figure that out. All right, let's keep cruising through this stuff here. So another of Boole's laws of thought rules, disjunction, or what us coders call OR. Here's the truth table. It's just OR. Produces a 1 when at least one of these guys is 1 on the input side. And let's see. So here's a couple of propositions. Ross went to McDonald's. That's a proposition because I either did or I didn't, right? So that makes it a proposition. Ross went to Chick-fil-A. Once again, another proposition. So there's this compound proposition, the disjunction of P and Q. You could just say P or Q, or the disjunction of P or Q. Ross went to McDonald's or Chick-fil-A. So this statement here would be a lie if I just didn't eat lunch. Basically here, as long as I went to one of these guys or both, then I'm not lying to you when I come up to you and tell you this, right? If I say Ross went to McDonald's or Chick-fil-A, I'm telling the truth as long as I actually went to one of those or both, right? So I could go to both and I'm still telling the truth as long as I were really hungry. Okay, then we got exclusive disjunction or XOR. So Dan went to McDonald's, Dan went to Chick-fil-A. The compound proposition here, P XOR Q, is Dan went to McDonald's or Chick-fil-A, but not both. So in English, we have to tack on this little piece, but not both, because we don't have a XOR in English. That's another problem with this whole logic thing. Is sometimes it's not clear what people mean when they use these logical operators in English. So here's an example of when this guy's ambiguous. Let's say you go to the Burgers, Fries, and Beyond down at the local mall, and you get a hamburger, and the clerk asks you, would you like mustard? He says, would you like mustard or mayonnaise? There's nothing wrong with having both, right? In that situation, it's not like you have to choose between these two. You can have both, right? As far as hamburgers are concerned, it's totally cool. So they're basically mean disjunction or inclusive or. They mean this or, right? It's okay to have both. But let's say your girlfriend, uses this phrase. So you can date Betsy is one proposition. You can date me, but let's say she uses or this way. She says you can date Betsy or you can date me. Not always, but typically she means exclusive or. That is, it's not okay to date her and Betsy. But she's not saying, but not both. So the problem here is that in English, the logic, the meaning of the logic is sometimes ambiguous. And this is just simple little statements. I think you may be able to imagine or appreciate that for a long chunk of dialogue, it's just very difficult, if not impossible, to extract that out as a very logical thing. Other than some kind of game that you're playing, some kind of debate game or something, as far as really arriving at truth or arriving at understanding between two people, I'm very much a skeptic on that. But another interesting thing, think about this. How much of this is hardwired and how much of it is not, right? Like, if a kid asks, can I have a chocolate bar or a lollipop or something, at the grocery store, where they put all the candy down where the kids can, see them. Let's say you say you can have chocolate or a lollipop, and then so they grab both, and then you take one away from them, and then they start crying. Are humans more wired for exclusive or are they wired for inclusive or? It's something to think about. Maybe kids are just spoiled. I don't know. All right, moving right along. Okay, so we can add a little more notation here so that we can develop this a little bit further. So we have something called a compound proposition. It's an expression composed of logical variables and operators like this, where you have a capital letter representing the compound proposition, and then you have these little letters representing smaller propositions. And then you can expand that into a series of smaller propositions and operators, and that's going to yield a particular true-false value in the end. Okay, so the capital letters are for the compound proposition, and the lowercase letters are for the little propositions. And here's an example. Here's an example of this thing. So we could have the compound proposition, capital P, is a function of the little propositions P and Q, given by this just arbitrary sequence of operations. So we have not P or Q and not P. And there's precedence to these things. So not has the higher precedence, and has the next highest precedence, and then or has the next higher precedence. So the parentheses are added here to show who has higher precedence. So we have the parentheses around the not because you do that first, and then parentheses around the and because you do that next, and then you have to do this guy before you can do the or. Okay, and so you take the result of this and the result of this, and you or those two together. It's kind of like exponentiation, multiplication, addition. It's the same idea with precedence there, which I'm sure you're already familiar with from coding, right? Okay, same idea. So this is kind of a mess, and even this is not so bad. So we can shorten up these symbols by using the tick for a not, and using a plus sign for or, and using juxtaposition for and we can express this guy here much quicker with this thing here. And we still have the precedence rules. You have to do not first. You have to do the P not first. Both of these P nots first. Then do the and right here. Then do the or lastly. All right. So there's different notations for the same thing, and this is more of the classical logic notations, and this is used in digital logic, and it's a lot more compact and easier to deal with, in my opinion. But we want to I don't know, pay homage to the classical philosophers. So we're going to use this notation in the book and elsewhere. All right, so here's an example of a compound proposition with three logical inputs, or three little propositions as inputs, given by this little expression here, P and not Q or R, which if you throw in the parentheses, looks like that. Anyway, yes, here's the function diagram. So this guy here, I'm calling the set A. It's really just the Booleans again, but A is the set of possible Boolean values, truth and false. And the compound proposition capital B is a function that basically maps the Cartesian product A cross A back into the set of Booleans, true, false. And it looks like this. You have these set of ordered pairs where the first element of each ordered pair is, in this case, a triplet. 0, 0, 0 is the first input, and then the output is 0. So this is a relation. Also happens to be a function because it's 1 to 1 and on to. And we can express relations as a table, right? We saw that when we were doing relations way back when. So what you can do is you can list all the possible true and false values of these little propositions P, Q, and R, which is what these binary values represent. We're basically just counting to 7 in binary here. 0, 1, 2, 3, 4, 5, 6, 7. And if you look, there's a pattern to these. There's 0, 1, 0, 1, 0, 1, 0, 1. So the first column's alternating every row. And then you have 2 zeros and 2 ones, 2 zeros and 2 ones, and 4 zeros and 4 ones. So that's a quick way to generate these tables. So that's the quick way to generate the inputs to these tables, is just follow those patterns. Now the output, how do you generate the output? Well, you have to just plug in each of these input values and work it out. So for example, you know, capital P of 0, 0, 0 is going to be, well, let me write the whole expression out. It's P and or not P and not Q or R. So you put in the zeros in there. So this becomes 0 and 1 when you do the not, or 0. And then we have to do this first because it's and. So we get a 0 and then or 0. So the answer is 0, which is the first element, first row in the table. So you do that 7 more times, you get all of these. Okay, so let's see, we're going to go on to logical equivalence. But what we're doing here is making a table of all the possible true and false values. So, yeah, I'll just leave that right there. So here I did it by hand. I evaluated it for one piece by hand. It's a little bit better sometimes to show the intermediate values here. So this is, I don't know, is this a different expression? Yeah, this is a different expression, but we have this compound proposition, capital P, which is a function of the smaller propositions, little p and q, expressed by this series of operands and operators. I have not p or not quantity p and q, just an arbitrary expression. So these are all the possible values of p and q expressed using true and false. Once again, to pay homage, am I saying that word right? Homage to the philosophers. This is the way they did it. They didn't use 0 and 1, they used true and false, because they hadn't invented binary computers yet, I guess. Yeah, that's in fact, they hadn't. Anyway, and it's upside down, so this would be 1, 1, 1, 0, 0, 1, 0, 0. So it's upside down from binary, but that's the way they do it. And then they break this apart operation by operation. So here's P and Q, okay? There's the column for that. And then the next thing you need to do is this, is negate that. So that's this column. That's the quantity P and Q negated is this column, and then you got to do this this thing here. You know, that's the next priority, right? Just do that. Then you can do the OR thing lastly. So you do the AND. So true and true is true, and otherwise it's false. That's doing this. It's just applying AND to these two guys, these two values. Okay. Then you not that whole quantity, which would be just flipping this column. So instead of true, false, 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 it would be false, true, true, true. Okay. Then you need to do this not P, which is just flipping this column. So instead of true, true, false, false, it's going to be false, false, true, true. Then to get P is just the ORing of these two things, or the ORing of these two columns. Right? So to get the final result P, you OR these two columns. So to do OR here, you just need one true in one of these. So here's a true, so bring that across. Here's a true, which is enough, bring that across. Once again, a couple of trues, there's the true. Right? So we're just applying OR to these two columns to get this guy here. Okay, so that's just a more detailed way of generating the 0, 1 things in a table instead of having to work it all out, you know, more algebraically. Okay, the value of this is it lets us determine something called logical equivalence. Okay, logical equivalence. All right, so here's the definition of logical equivalence. So two compound propositions, capital P and capital Q, are logically equivalent, and we use this symbol, three bars, so it's like an equal sign with 3 lines instead of 2. If their truth values are identical for all combinations of the inputs, the little PQR inputs. So we just look at the class columns here for P, for capital P, and we're going to have a capital Q. We just look at both of those. So here's an example. Okay. So let's do some poetry here, right? So roses are red is our little proposition P, little p. And then we got another little proposition, violets are blue. Okay, so we could say all kinds of things with that. We could throw some more English in there and start nodding and anding and oring and saying all kinds of wonderful poetry type stuff. So for example, one thing you could say is capital P. You could say it is not the case that quantity roses are red and violets are blue. So you don't agree that roses are red and violets are blue. You know, you're saying that. Or you could say roses are not red or violets are not blue. You could say that. So big P is a compound proposition and big Q is another compound proposition. So before we move on, note that these parentheses, you know, nobody talks like that. You know, so that's one ambiguity when you're speaking, is where do the parentheses start and where do the parentheses end? So right off the bat, you know, you're running into a problem with translating English into symbolic logic. And language changes over time. People have different intonations and emphases that they're making. People misspeak, all kinds of crazy stuff. So just pointing out the problems, the pitfalls with this kind of thing. But for us logicians and computer scientists, you know, we just want to know, are these two things logically equivalent? In other words, are you saying the same thing logically when you say these two lines? Are you? Okay? The way to do that is bust it up into a table here. So you need the logical expression for this thing. Roses are red and violets are blue with a not in front of that whole quantity. And then we need the logical expression for this thing. That's on the next page here. There they are. So it is not the case that roses are red and violets are blue, right? And then this dude down here is roses are not red or violets are not blue. So you construct a truth table with all the minding your P's and Q's, as they say, with all the values of P and Q, true, 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 false, false, true, false, false. Then you break out the pieces of each of these things here. So you need a not P. Here it is. You need a not Q. Here it is. Then you OR those two together, and you get, where is that? You get this thing. That's just these two ORed together. And you can't see that this is green because my printer is goofing up again. But this is what you get for Q. You get false, true, true, true. Likewise, you do the AND part on just P and Q. So you're going to AND these two columns together, and you're going to get this. And then you knot that whole thing to get this, which is capital P. Okay, and then false, true, true, true is the same as false, true, true, true. So these two statements, capital P and capital Q, are logically equivalent because they have the same truth values for all values of little p and q. So they're logically equivalent. They're kind of saying the same thing logically. So you're being redundant if you're trying to woo your romantic interest by repeating these statements. You know, like if you're dating somebody and it is not the case that roses are red and violets are blue, and then you say roses are not red or violets are not blue, your romantic interest might say, you're just being redundant, All right, just a little stupid joke. All right, so anyway, the P and Q columns are identical, thus these two expressions are logically equivalent, or expressed as broken out, or expressed as just the P and Q, the big P and big Q. All right, logical equivalence. By the way, this is De Morgan's. Remember De Morgan's from set theory. Remember De Morgan's, what do? You just reverse everything. So this OR, oh wait, that's an AND. This AND becomes an OR. The individual little props, which are not negated, those become negated. And then the quantity here, the entire quantity, which is negated, the quantity around here, which we don't need the parens to show that, but the entire quantity is without negation. All right? That's De Morgan's. Okay. So what have we done? We've done and, or, and not, right? And, or, and not. Now, there's a couple more logical operators, which I call funky logical operators, because they start to get hard to understand, at least in terms of the English, and therefore maybe perhaps less useful. So I want to point out, if you're having trouble making this stuff make sense, well, the stuff so far should make sense to you, but now the stuff going forward, if it's starting to be a little bit weird English-wise, don't worry about it, just do it. There's historical context, language changes, other things that could be influencing what's going on. But so Mr. Boole, George Boole, had this operator called implication, or what he called conditional proposition. And there's different notations. There's this P arrow Q. There's P implies Q. There's if P, comma, then Q. Sometimes they say P is sufficient for Q. Q is necessary for P. So in certain contexts, this works perfectly, like proof by contradiction, this stuff works. But there's other contexts where you're putting English into it, where it's debatable whether it's clear, working properly. In my opinion, you can arrive at a consensus on how to deal with them, but it's useless. It's useless. All right. Here's the truth table for this thing. This is the pattern of ones and zeros for implication, also known as conditional proposition. And the way I remember, once again, is the acronym TFF. Or I don't know if that's an acronym, but somehow I can remember that. And it's just TFF, and then the rest of the output column is ones. So Here's a couple of examples here. So little proposition P, it is sunny today. Little proposition Q, we will go to the beach. So according to Boole, when somebody comes up to you and says, if it is sunny today, comma, then we will go to the beach, they are implying something. And Boole, being, you know, the super logical guy that he is, would require you to use that truth table we just saw. That's the way to do this. Just agree with this particular use of language and do the translation. Don't worry about whether this makes sense in the modern context, the way people use language. It doesn't even matter. Someone could also say this statement: we will go to the beach if we will go to the beach is necessary for it to be sunny today. That's also implication, right? Okay, there's another one here, biconditional proposition, which is another one of these funky truth tables. It looks like not XOR. It's the opposite of XOR. That's easy to remember. But Boole claims that this set of language is using bicondition when people say things like this. Okay, so keep that in mind. Next time you say something like this, you're using bicondition, whether you meant it or not. Oh, and what I mean is just follow the rules and do this. Whether this has modern day applicability is not the issue here. So, for example, someone could say this thing here, like, so given this little proposition, 1 is less than 5, which is a proposition, happens to have a value of true. So remember, once again, there's a difference between whether something is a proposition and the subsequent true or false value of that proposition. So 1 less than 5 is a proposition because it's either true or false. Then the truth value of this happens to be true. That's a separate thing, because 1 is in fact less than 5. So 2 separate things. Okay, here's another one. 2 is less than 8. That's a proposition, happens to be true. So someone could say this compound proposition: 1 is less than 5 if and only if 2 is less than 8. And according to Boole, when you use the phrase if and only if, then you're doing bicondition here. So that would be true, because according to the truth table here, the last row, true and true for little p and q, results in true for the output. Okay, so the compound proposition is true on that. Just apply the truth table. I think in the book they're gonna, they ask you to, they give you these English sentences and they ask you to turn that into symbolic logic. Just apply these rules right here. Don't worry about whether they make sense English-wise. Just apply the rules. And then as far as evaluating the true or false value of the algebra, then just apply the truth table. So, let's look at another example before we move on with where this starts to fall apart. Is this thing here. So 1 is greater than 5. That is a proposition because 1 is either greater than 5 or it isn't. So that makes it a proposition. This particular proposition, 1 greater than 5, happens to have a value of false in the real world. Okay. Then this proposition, 2 greater than 8, that's a proposition because it either is or isn't. And in the universe I live in, 2 is 2 is not less than 8, so this is false. So if someone said 1 is greater than 5 is necessary and sufficient for 2 being greater than 8, then they're doing this. So they're using implication here. So this English statement, according to our rules that Boole laid out for us, is bicondition, and just go with that. And then from our table, this compound proposition happens to have the value true because of the truth value of the input propositions, which are false. So because we're on this row now, right? Little p is false, and little q is false. Little p is false and little q is false. Therefore, the compound proposition p by condition q is true. Okay. So, just to drive the point home that applying this to natural language has problems, let's look at another example here of a couple of things here that happen to be logically equivalent and are interesting to look at. So we have P implies Q, which happens to be logically equivalent to not P or Q. And you could prove that with a truth table, as we looked at earlier. We could prove that these two are logically equivalent. And then we also proved, in fact, we proved this right here. That was, no, it was slightly different than what we proved. But this is another example of De Morgan's right here, where between these two, everything is flipped, right? The not P becomes a P, the Q becomes a not Q, the or becomes an and then the whole quantity becomes knotted. So this is another version of De Morgan's. So these are logically equivalent, and this one's also, all three of these are logically equivalent, which you could prove with a truth table as well as observing that it's De Morgan's. But let's break this up into smaller compound propositions, A, B, and C. So just breaking this guy up into A, B, and C. And then evaluate it for truth. So let's put in some proposition, some little propositions. Pigs fly. Okay, that's P. And 2 plus 3 equals 6. So those are propositions, because either pigs fly or they don't. And 2 plus 3 equals 6. It either is or it isn't. So that makes them propositions. So we can use them. We can only use propositions on this. So we have to make sure everything is a proposition. These two propositions in the universe that I live in, the part of planet Earth that I live in, I haven't seen a pig fly yet. Not that I've really been watching, but I haven't seen one fly. So it's false. And so far, every time I've punched in 2 plus 3 into my calculator, it's always come up 6. I've even used my fingers, and it comes up 6. That is, it doesn't come up 6. Sorry. Concentrating on form, not content. Yeah. So these are false. So applying the truth tables to these, then you get for A you get various English statements that are of varying degrees of confusabilityness. Okay, like A is P implies Q, and if you just plug in the false into implication truth table, you're going to get true. So this basically is saying the statement, in the universe I live in of non-flying pigs and this arithmetic, if pigs fly, then 2 plus 3 equals 6 is true. Maybe as sarcastically or something, that kind of makes sense, right? Like, if pigs fly, then 2 plus 2 equals 6, sort of makes sense, kind of. Okay, or we've already established that these are logically equivalent. Then you could also state compound proposition B in English something like, well, it's exactly like pigs do not fly, or 2 plus 3 equals 6. Now, that's true, but does that make sense? English, it's harder to make sense out of that English-wise. And then the last one, it is not the case that pigs fly and 2 plus 3 equals 6. Maybe that makes a little more sense, and you could agree that's true. But the point is these kinds of things start to get confusing, and maybe that limits their applicability a little bit. All right, but don't worry about it. All right, if you like this and you like dealing with this, you can major in philosophy, and that's awesome. For us coders, we don't have. One way to talk about it is we can't tolerate this kind of ambiguity. We have enough things to worry about just getting our semicolons in the right spot. All right. So let's see. Yeah, anyway, oh, hey, here's the table that proves that these guys are logically equivalent. Awesome. Yeah. All right. So one last example. So once again, Boole laid down the law and said that when people say stuff like this, they mean implication, and this is what they mean logically, and you hold them to it. Hold them to it. That was his attitude. So here's another example of basically just applying these rules that were given, and once again, don't worry about whether that really makes sense or people really talk this way. But if you apply these rules, then given the little proposition P, you drive over 65, and Q is you'll get a ticket. Then if someone says this, if someone says you drive over 65 and you will not get a ticket, then that's what they mean symbolically, right? P is you drive over 65 and not Q. So Q is you will get a ticket, so you will not get a ticket, right? That's this. Then if they said something like this, you will drive over 65, or I'm sorry, I misspoke. You will not drive over 65, or you will get a ticket. They're saying that. And likewise, here's this. If you drive over 65, then you will not get a ticket. That's this if P then Q thing with Q negated. Okay, and then there's some other ones in here that you can kind of go through. But look, the point of this, and here's another limitation of this logic. Another point of this is, you guys know that you're not supposed to drive over 65, right? I mean, you know that. So, what is this? You're just trying to prove logically to somebody that they shouldn't drive over 65. I mean, you guys know that you could get a ticket or you could crash. So, once again, I'm just trying to iterate to you my particular opinion on the usefulness of logic. We certainly need it in computers. They are nothing but logic. Humans, on the other hand, it's good to study logic. It's good to have that in your toolkit. It's good to think logically about things, but there's a whole lot more going on in being a human than just being logical. All right. Hope that was useful to you. See you next time. Bye.